So please write down the heading energy stored in a inductor. So energy stored in an inductor. Now, what is the energy stored in an inductor? Suppose you have an inductor of inductance, and let's say initially the current is zero. And if the current is initially zero, and let's say at any general instant of time, a current I is flowing, so what will be, and let's say this current is growing, okay? The current is increasing in nature. If this current is increasing in nature, then what will this inductor do?
Try to decrease it.
It will try to decrease it by inducing a polarity in the opposite direction, right? So
Yes,
if I
sir.
say there will be a positive over here and there will be negative over here, then only there will be polarity. Then only this battery will be opposing this current, right? Are you getting my point? And
Yes,
what is
sir.
the EMF of this? The EMF is L into di by dt. The sign we can use, the sign we can guess using Lenz's law. And, you can write the magnitude of this EMF, right? Yes or no?
Yes, sir.
Ah, so tell me this particular thing, what will happen when the current will get into the battery, then work will be done on the battery, right? And what will do the external work? Some external source will do the work, right? Yes or no? So again, always remember, whenever we talk about potential energy stored in any particular thing, we always try to do with the work done by external agent, right? So when power is supplied to the inductor, what power is supplied, guys? The power will be basically whatever is the EMF across this particular thing, E multiplied by whatever the current flowing. So E multiplied by, so that will be equals to I into L into di by dt. Yes or no? Can you see this is your E and this is your I? Will this be the power? Yes or no? Is this the power supplied to the inductor?
Yes, sir.
So can I say the energy absorbed by the inductor in time t, in time dt, will it be equals to du, and that will be equals to what? Power multiplied by time. Can you see energy is basically power multiplied by time? भाई ये कनेक्ट नहीं है, वो कनेक्ट नहीं है, इट्स नॉट कनेक्टेड. देख जरा बंद हो जाएगा वरना पीसी मेरा. गाइस 2 मिनट्स, गिव 2 मिनट्स. इट्स नॉट. ये बंद है, उधर से बंद है. इधर से कैसे, इधर से बंद कैसे? हाउ इज इट? उधर से बंद. हाउ नहीं पकड़ रहा है. कौन? इसमें इसके अंदर लाइट ग्लो होता है. Guys, just give me 2 minutes. Let me sort out this issue. ये तो नहीं, मेरा पीसी इसे बताता नहीं. How? Yes, guys. Hello. If we wouldn't have acted a little bit later, तो class बंद हो जाता. फिर उसके बाद चालू करना पड़ता है. So, anyways, everyone is able to see my screen, right?
Yes, sir. Yes,
Okay.
sir.
एक सेकंड मेरे को पेन भी लाने दो. Okay, Satvik. Okay, Ishita, no problem. So du is basically p into dt. Now what to do? Power क्या था? ये रहा. So it will be L into I di by dt multiplied by dt. Yes or no? Yes or no, guys? This dt and this dt will get cancelled, and the energy is basically L into IDA. Now what will you do? If
Induction.
initially no current was passing through the inductor, and it rises from 0 to, let's say, I naught, or 0 to, let's say, what shall I give? 0 to capital I. I is the general current at any instant, and let's say 0 to I it has increased. And the basically initially no current, and finally the current has increased to I is equals to I after a certain time. Okay, so the potential energy will be equals to the integration of this du, which will be integration of this Li di from where to where? From where to where, guys? From 0 to capital I. So when you integrate this, you get I square by 2, and you put the limits, you get capital I square by 2 minus 0 square by 2. So ultimately the final answer which you get is this. Please remember, it doesn't depend upon time. So even if it is at any general time or after a long time, doesn't matter. If the final current flowing through the inductor is I, then have Li square. Is this clear?
Yes, sir.
This is the energy which gets stored is in the form of, this energy is in the form of what kind of energy?
Magnetic energy
Is
or flux.
magnetic field energy is in
Field
the
energy.
form of magnetic field energy. I told you, wherever there will be a field, there will be some energy associated with it. That kind of
With the
energy.
capacitor.
Do you remember the electric field energy? Electric field energy, half epsilon naught E square. इसको याद है? Electric
Yeah.
field energy density is this. So the
Yeah.
same kind of relation is also over here. We'll write that once you're done with this. Just tell me.
So since a capacitor harbors an electric field, it also stores energy in electrostatic form, right?
Electric field energy, yes. The half CV square can be equals to half epsilon naught E square multiplied by the volume of the capacitor, the volume of the space inside the capacitor. See, if I have a capacitor C, and let's say the potential difference across its V, so can I write the electric field which gets set up inside is equals to V divided by D. Yes or no? The potential difference across the capacitor divided by the D. And if I say, what is the this particular thing? Half epsilon naught E square is the electric field energy density. This density multiplied by the volume. What is the volume? Area multiplied by. So when you do this, see, don't need to write this in a capacitor thingy. We already discussed this in electrostatics. So half epsilon naught A. Can you see this will be D square and this will be D. So D into V square. And what is this? C. So can you see the electric field energy inside is equals to the potential energy stored inside the capacitor. Same way. Okay. Shall I erase this part? So please write it. So magnetic field energy density you can write similar to electric field energy density, which is equals to half epsilon naught into E square. Magnetic field energy density is given by half B square by mu naught. Okay. Please write this formula. Always remember this magnetic field energy will always be in joule per meter cube for SI units. Okay. उधर का पोर्ट पता नहीं चलने रहा उसमें मेरा वो फंस गया डन so whenever you're done just tell me Acha, and give me 2 minutes also just give me 2 minutes I'll be back 100 done hello guys are you done
Yes, sir.
please write down and ये वाला जो the one thing which अभी we are doing it's a very important derivation as per your school so field energy of magnetic field in a current carrying inductor or basically in a current carrying solenoid So suppose guys there is an inductor through which the current flowing is how much? I. Okay. If I say the area of cross section, the area of cross section of the inductor is A, the length of the inductor is L. Sir, why do we need length? Because to give the volume of the inductor. Okay. Yes. Can anyone tell me what is the magnetic field inside the inductor? Inside the inductor. If the number of turns is. So guys, how will you write the statement? Can anyone tell me how will you write the statement inside? How will you write the statement of this derivation? Let us consider a current carrying solenoid with number of turns n, length L, area of cross section A, carrying a current I. Yes or no? So do you remember the magnetic field inside this long solenoid, was it equals to n by L, the number of turns per unit length, multiplied by mu naught n I, mu naught small n into I? Yes or no? Everyone remembers the formula?
Yes, sir.
Is it the
Yes,
same
sir.
thing?
Yeah.
So what is the total field energy inside? Total field energy inside, will it be equals to magnetic field energy density multiplied by volume? Can I write it like this? So magnetic field energy inside will be half B square upon mu naught. The volume, what is the volume? Area multiplied by length. The same thing I'm doing, right? So half,
Yeah.
what is the magnetic field? Mu naught into n by L into I whole square divided by mu naught into A by L into A into L, right? And when you will solve this, you will get half as it is. This mu naught will become square and one mu naught will get cancelled to mu naught idhar. उसके बाद can you see n square? There will be this L square will be in the denominator, but one L will get cancelled with one L and only one L will remain in the denominator. And this area A also I am bringing over here into I square. And if you remember, this thing is nothing but the self inductance, right? Guys, is this thing nothing but the self inductance? I'm taking the length as small l, okay? Just to avoid the confusion. So this thing is nothing but L, half L I square. So can you see the magnetic field energy inside? The magnetic field energy is basically equals to the potential energy stored in the inductor. So always remember the expression for field energy inside the solenoid or inside the inductor, whatever you want to say, is the same as the energy absorbed by the solenoid during the growth of current. Is it clear, guys? Or we can say what? We can say the energy is stored in the form of energy stored in inductor is in the form of magnetic field energy. Just like for a capacitor, we can say that the energy absorbed by the capacitor is in the form of electric field energy. Similarly, for an inductor, we can say the energy stored in the inductor is in the form of magnetic field energy. Please remember the way capacitor behaves in case of electric systems, the same way inductor behaves in the case of magnetic systems. Okay. Yeah. Phone. Then.
So, sir, when the current is stable or when it's constant, there's no additional field energy absorbed by the solenoid.
No. एक बार करंट बढ़ना बंद हो गया तो उस पर्टिकुलर इंस्टेंट तक जितनी एनर्जी स्टोर हुई है दैट इज इक्वल टू हाफ एल आई स्क्वायर.
So for inductor, as long as there's a change in magnetic flux, then there'll be energy stored in it.
For an inductor, as long as
there's a change in magnetic
energy
flux.
will keep on getting stored.
Fine.
And as it is, as जैसे करंट कांस्टेंट हुआ तो एनर्जी भी कांस्टेंट हो जाएगी.
Okay, because as long as there's current flowing in it, there will be dissipation of energy. So that's why energy won't be constant.
Dissipation of energy will not take place on inductor. It will take place on resistor.
Resistor. Yeah.
इसमें सिर्फ स्टोर होगी जैसे कैपेसिटर में एनर्जी keeps on storing, no? The same way inductor also keeps on storing energy till the time current keeps on increasing. Once the current is stopped, it will stop storing further energy. So whatever energy is being stored, it will be there. फिर आप you can use that energy somewhere, just like a capacitor. ठीक है?
Okay.
Okay. So I'll give you one question based on energy field density. One more question. This is also, this can be also asked as a question only. So everyone remembers if there is a current carrying sheet, what is the magnetic field? Guys, do you remember if there is a current carrying sheet? I'll give you the formula at least if you don't remember. Suppose there is infinitely long current carrying sheet with current per unit width as small I ampere per meter. Okay. And I want you to find out, there is an infinitely large sheet. Okay. So I want you to find out the magnetic field energy stored in a cubical region. Find the magnetic field energy in a cubical region of side A. Near the current carrying sheet. And for those who forgot what is the magnetic field due to a current carrying sheet, I'll remind you. The magnetic field due to a current carrying sheet is given by half into mu naught into small I. Okay? This I ampere. So magnetic field is given to you. You just need to multiply you need to use this magnetic field and calculate the energy. How will you calculate the energy? Energy field density multiplied by the volume, right? Are yes or no?
Yes, sir.
Chalo, fatafat find out the answer. ये डॉट हटा दो, किसका है? Guys, can you also see this dot?
Yes, sir.
Yes, sir.
भाई जिसने ही बनाया डिलीट कर दो. So the electric field energy stored will be basically again equals to what? Energy field density half b square by mu naught multiplied by the volume. So it will be half b square will be 1 by 2 mu naught into I square by mu naught into volume will be a cube. So this will become 1 by 4 multiplied by 1 by 2, it will become 1 by 8. Mu naught square and 1 mu naught will get cancelled. Mu naught I square a answer. Joules, by the way. Check. That's the answer to this problem. So anyways, please write next heading, mutual induction.
Sir, I have a doubt.
Bole?
Sir, half Li square is also magnetic field energy, right?
Yes, it is.
And half mu naught n square I square a by L is also magnetic field energy. Like that formula that we use now. The energy density into volume.
Volume, yes.
So when they ask for magnetic field energy, which
whenever they will ask for that, please remember that half Li square, no, that is the energy stored inside an inductor during growth of current. Okay, that is stored in the form of energy field, magnetic field energy. That is a different thing. So are you getting my point? This energy is different, this energy is different, but in the case of an inductor, this energy is equal to that energy. Are you getting my point?
Oh, okay.
Okay.
Okay, sir.
So
Okay, sir.
ऐसा relate करने की try to do a little bit. Okay. So what do you mean by mutual induction? Obviously the name includes mutual, so it's not like only a single entity will be doing things, right? So always remember what is mutual induction. It is the property of a pair of coil. Property of a pair of these, due to which the change in current in one coil is opposed by the EMF induced in the other coil. Are you getting my point? Change एक में होगा, but other will say no bro, don't do this. I don't want you to change. Okay, suppose there are two friends who are sitting in a club. One is saying no, I'll drink more. Then the other will say no bro, don't do it. One is saying I'll drink less, so no bro, drink more. Are you getting my point, guys?
Yeah.
So the other will say don't change. Don't change, just be on constant whatever you're doing. So suppose there is one coil like this and another coil like this. Okay, so suppose the current through this coil is, let's say, I1. So what will happen? This current I1 is, let's say, I1 says I will increase. The current flowing in the first coil is I1, and let's say I1 increases. If I1 increases, then what will happen? The flux produced by the first coil, will it increase? So whatever will be the flux inside the first coil, will it increase? Yes or no? Yes or no,
Yes,
guys?
sir.
There are two coils. The first coil, what happens? There was a current flowing in the first coil, and suddenly now this current starts increasing. If the current starts increasing, then the flux associated with the first coil will increase. Yes or no? Yes or no?
Yes, sir.
Now the same flux is linked with this coil as well, right? Some of the flux is linked with this coil as well, right? So phi 2 will also say increases, right? Initially it was 0, or initially it was something, but when this current is increasing, automatically the flux associated due to the current in the first one is also increasing in the second one, right? I'll write the whole thing so that you won't get confused. If I1 flows in first coil, it produces flux phi 1 in the first coil. This flux phi 1, or basically we can say a part of this flux, that part is basically what? Phi 2. Yes or no? Now if I1 increases, then phi 1 also increases. Yes or no? And if phi 1 increases, automatically phi 2 will also increase. Yes or no? Yes or no, guys? Guys, are you able to follow till here? If
Yes,
I1
sir.
increases, then phi 1 increase, and phi 1 will increase, then phi 2 will also increase. So what will this loop say now? No bro, don't do this. If you are doing this, that's why I'm suffering. I don't want you to do it. So basically what he will do, he will try to oppose this particular thing. Yes or no?
Yes, sir.
So basically what will happen? Due to this opposition, an EMF will be induced in the second coil. So the second coil will oppose the change in current in the first coil by inducing an EMF inside it. Please remember, the second coil is not inducing any EMF in the first coil. The second coil is inducing EMF in itself to oppose the change in the current in the first coil. Are you getting my point? Shall I again take you back to that example? Keep, bro, don't drink much. If you keep on drinking, then I'll drink. So this is a kind of dhamki which the second coil is giving to the first coil. Are you getting my point, guys? समझ में आ रहा है थोड़ा बहुत?
Yes, sir.
Yes, sir.
Okay. So remember this example so that at least you will get to know yes, what exactly is mutual induction inside itself, inside the second coil itself. I'll write clearly inside the second coil itself. Okay. Please remember, why is it doing the opposition in the change? It is because it is in accordance with Lenz's law. Okay.
Yeah.
So suppose there is this first coil and suppose there is this second coil. Whatever current is there, I1, due to which phi 2 is getting affected, then we can say this particular thing, this phi 2 is directly proportional to the current in the, do you remember in self induction, the current, the flux in the same coil was proportional to the current flowing in itself. In the case of mutual induction, the flux in the second coil is proportional to the current flowing in the first. Okay. And when you remove the sign of proportionality, you introduce a constant, but this constant won't be equal to L because L was self induction. This constant is basically called as the coefficient of, where M is called as the coefficient of mutual induction. The SI unit is again same as the that of dimensional formula, everything same. Okay. But remember this particular thing, the note करके लिख देता हूँ मैं. The value of M depends upon the flux linkage between the two coils. So how the flux, how phi 1 is related with phi 2, उस पे ये M की value will depend. And we'll see various series example, we'll see how exactly it will. Okay. Yeah. So once you're done till here, just tell me, then we'll start. We'll write some points regarding mutual induction. हाँ, बना लो, उबाल लो. Done, guys, done.
Yes, sir.
Some important points about mutual induction. First point, M is a bidirectional coefficient for a pair of coils. Sir, what do you mean by bidirectional coefficient? I'll tell you what exactly I mean. Suppose if this is the first coil and this is the second coil. First and second. If I flow some current in the first coil, so phi 2 is there, yes or no? So do you remember I wrote this as phi 2 will be equals to M into I 1, yes or no? Similarly, if suppose this is the first coil again and this is the second coil, and if now some current is flowing in the second coil, let's say I2, due to which some flux is generated in the flux is linked with the first coil, then again I'll write phi 1 is equals to M into I2. This is what is meant by bidirectional, whether current is flowing in this or whether current is flowing in this. This M will be same for both these coils. The same coils were there, right? Till the time the coils were same, so it doesn't depend upon whether the current is flowing in the first coil or the second coil. Is it clear? You understood what does bidirectional coefficient? If the pair of coil is same, then you can use the same M for both of these coils, whether you current flow is this and this. Doesn't matter. Shall I write it? M will be same if we want to calculate flux in second coil due to current in first, or vice versa, or in both cases. Shall I write it like this? M will be same if we want to calculate flux in the second coil due to current in first. Or vice versa. In both cases. Clear?
Yes, sir.
Acha, tell me, if current is flowing in both coils, if current is flowing in both coils, then what will you do? Then we need to consider the flux due to self-induction as well while considering the flux, not while considering, as well as the flux due to mutual induction. So are you getting my point, guys? If there is current which is flowing in both the coils, let's say here the current is I1 and here the current is I2. Okay, then if I want to find out what is the flux in the first coil and the flux in the second coil, then I'll write flux in the first coil will be because of the current in itself, so L into I1, as well as the due to the mutual induction of this current I2, so M into I2, and here we'll write plus minus because there is a reason for it, although मैं बताऊं कि नहीं बताऊं, that's the question. because that dot convention is no longer there in syllabus, but still you can write this as plus minus. Or if I want to calculate what is the flux in second, the L2 into I2 plus minus M into I1. Yes, tell me.
So shouldn't the direction of current be in the other way around? In the
No, it is an external current flowing in both the circuits. I1 and I2 are external currents, and not necessary ki, it depends. All depends upon whether it is increasing or decreasing.
Oh, okay, sir.
So can you see over here, guys? For since the pair was same, so can you see M value is same for both the cases? The value of M is same, although this is changed. That doesn't matter. ये तो इनका individual है, right? Check. Sorry. Sorry. Guys, give me 2 minutes. Hello. Hello.
Yes, sir.
Check. Please write a heading, a relation between self-induction and mutual induction. Always remember, suppose if I have a one coil and there is another coil. Okay, the self-induction of this coil is L1 and the self-induction of that second coil is L2. And let's say the mutual induction between them is M. For both the pair of this coil is M. Okay, then there is a relationship between this mutual induction and this thing. K times of under root of L1. L2. This K is called as the coefficient of coupling. Out of syllabus things, guys, school level out of syllabus, hai na? They will just mention it. I think they have just mentioned the name, nothing more. This K is basically called as what? The coefficient of coupling. So what is the maximum value of mutual induction between two coils? It is L1, L2. Yes or no? And what is the minimum value? 0. When I'll use 0 over here, it will become 0. When I'll use 1 over here, it will become under root of L1, L2. Please remember, coefficient of coupling depends on the flux linkage. Depends on the flux linkage. That's why the value of coefficient of coupling varies. Suppose, sir, if I want to link 100% flux, for 100% flux linkage, what I can do? Either I can wrap one coil over another. मतलब क्या सर? मतलब ये. So can you see this? I have wrapped one coil over another coil. The coefficient of self-induction was this, and the coefficient of self-induction was this. If we wrap one coil over another, then this 100% flux linkage is there. Then K is equals to 1 and mutual induction is equals to under root of L1, L2. Okay. This is ideal condition, hai na? The second case can be what? What can be the second case, guys? Can you suggest any method through which I can just link the flux between them? Suppose if I have a soft iron core, if suppose this is a soft iron core bar over which I have wrapped all the, wrapped both the inductors. In this case also, K is approximately equal to 1, or we can say M is under root of. If there is no energy loss inside the soft iron core, then also here the coupling is 100%. Clear?
Yes, sir. So, what is coupling?
Coupling matlab basically when you play, how you place both of them together, how you couple them, how you use them together is coupling.
Okay.
So basically I'm using both of them together only, no? But see, I have different ways of using them. So how I'm coupling them together, the value of mutual induction varies.
Okay, sir.
For 0%,
but it's the same, right? In both the cases, it's the same.
In both the cases, we assume there is 100% linkage. For 0% flux linkage, I can give you certain examples. For example, if I have this coil and this coil, but I have placed them at a very large separation. If I place them very far away from each other, will there be any flux generated from the first one linked with the second? No, right? Almost negligible flux will be linked, right? So here we can assume M is 0 and K is equal to 0. Okay, this is one of the case. Or sir, I don't want to do this. I want to place them nearby only. But can you see over here? Suppose if I have this is my first coil, and let's say, this is my second coil. So can you see over here in this case, I coupled them in such a way that what happens now? Can you see the magnetic flux due to this will be like this, but those will be parallel to the area? Yes or no? So here no flux will be linked with each other. Here also K is 0 or M is 0. So when the coils are placed at a large separation or the coils are placed at right angles, then also there is no flux linkage between them, and hence the coefficient of coupling becomes 0. Clear? Is this clear?
Yeah. Yes,
Shall I give you some questions based on mutual induction?
Yes, sir.
Suppose guys there is a small coil. अच्छा, in spite of ऐसा ना करते. There is a very big coil. Can you see over here? The first coil is very big. Number of turns is one only. Circular loop, and let's say the current flowing in this is capital I. Okay. The current in this is in flowing is basically capital I. Concentric to this 1 2 3 4. Concentric to this is a small coil.
कांटेक्ट क्या करके सेव किया है?
क्या
इसका एक्सप्रेस वाले का पीपल करके किया है क्या?
नहीं, इसका नाम से किया है.
क्या नाम है?
इसका नाम क्या था?
एक्सप्रेस
हाँ,
पीपल
एक्सप्रेस से ही होगा. देख,
एक्सप्रेस करके
guys, can you see two concentric circular coils? Guys, can you see two concentric circular coils?
Yeah.
The bigger one has a radius capital R, and the smaller one has a capital small r radius. R is way bigger than small r. Okay. So a small coil of radius small r is placed at the center of another coaxial coil of radius capital R, where capital R is much greater than. Now the question is, find the coefficient of mutual induction for the pair of coils. How will you do it? First of all, can anyone tell me how will you find out the mutual induction? Sir, we can find out the mutual induction by this way. Not this, but just by the definition. Can you see over here? The current is flowing in one coil and the flux is generated in the second coil. So try to use this, try to find the flux in the smaller coil because of the current in the, as a function of current in the first coil. Acha, what is responsible for the flux in second coil? Tell me over here. What thing is responsible for flux in second coil? This is first and this is second. What is the flux? What is the cause of flux in the second coil? So the flux is caused because of what? Guys, hello? अच्छा ऐसे मत करो. Do reverse engineering. Tell me, if I have a circular coil in which some current is I, what will this current produce? Yes, what will this current produce at its center?
A magnetic field.
A magnetic field. That magnetic field, will it pass through the smaller coil? Will that magnetic field pass through the second coil, the smaller coil? Yes or no? अरे yes or no? क्या पहला coil, whatever the coil for one first coil is producing, will that magnetic field will it pass through the second coil? Second
Yes.
coil is at center. Yes. The way second coil से जब pass होगा, तो what will the second coil produce? There is some area related with the second coil and some magnetic field is passing through. So will there be any flux associated with the second coil? Are you getting my point?
Yes, sir.
So ऐसे करके we need to relate the magnetic field at center due to current in the bigger coil. Will it be equals to B1 will be equals to mu naught by 4 pi, and what was the current due to this? 2 pi I by R. Do you remember the formula? Does anyone remember this formula? P1 is this. Now the flux through smaller coil placed at center, will it be equals to phi 2? The magnetic field at the center is V1 multiplied by the area. And let's say what is the direction of magnetic field? What is the direction of magnetic field due to this?
Out of the plane.
Out of the plane. Out of the plane, yes. So let the magnetic field B1 is out of the plane. Let's say the area vector is also out of the plane. So if I do this, then cos 0. Right? But since we are all talking about magnitude, because we want to find out that, so mu naught by 4 pi into 2 pi I by r. This is the magnetic field multiplied by pi into small r. I'll take just this I outside, everything else inside. Pi ye se ye cut jayega, it will become 2. And this will be equals to mu naught by 2 into pi r square upon capital R. This into I, and that will be your phi 2. Do you remember, this is the first coil which is flowing in the first current, right? This is I1. If I compare, so can you tell me what is the value of M? So on comparing, M is equals to mu naught pi r square divided by 2. And that's the answer to this question. Are you getting my point, guys? I'll give you, shall I give you one more question like this? घर से करके लाओगे? Will you do it as a homework?
Yes, sir.
Anji, in spite of giving you circular, who is putting these dots? In spite of giving you a circular loop, I have given you a square loop.
Square.
The side of this is small l, and the side of this is capital L. And again, L is much greater than small l. ये homework है. Try to find the coefficient of, again the same question is same. Find the coefficient of mutual induction. So try to do this. Your chapter unit 3 MEC will be used over here. Okay, magnetic effect of electric current. And since I have taken this L as very small, so this smaller loop is very small, right? So we'll assume that the magnetic field is same throughout the whole thing. You will consider this square loop, smaller square loop as point of. Okay. Clear? Any doubt till here?
No, sir.
So these are your homework questions. एक last note करके we can write the total magnetic field energy stored in two coils. Suppose this is two coils, there are these two coils, this is L1, this is L2, and the coefficient of mutual induction between them is how much? M. So we asked what is the total energy stored. The question is what is the total energy stored. So if I say if the current in the first one is, let's say I1, and the current in the second one is, let's say, I2. So the energy is half L1 I1 square plus half L2 I2 square plus minus M into I1 and I2. Acha sir, tell me this particular thing. This has been enough now. Why are you using plus minus sign again and again whenever mutual induction is there? Always remember, the mutual induction which gets developed, it is not necessary it will always increase or always decrease. It depends on certain factors. इसका point काट देना, मेरे को पता तेरे को काम करेगा इसमें लेके बोल रहा था अपने पास क्योंकि वो एक्सप्रेस वाला कॉल करेगा। अच्छा वो मैं चलो लगा लूंगा इसको। So don't why is this plus minus? It's because यहाँ पे whenever we talk about mutual induction, there is the flux can neither not neither flux can either support it or flux can either oppose it. The flux due to mutual induction can either oppose or can either, what do we call it? Support. Yes. So that's why. Okay. So that's why we are using this plus minus sign. इसका एक डॉट कन्वेंशन होता है बट वो आउट ऑफ सिलेबस चीज है. Dot convention for inductors for defining magnetic poles. There is one more heading inside my notes. So abhi
Sir, that those topics won't be useful for JEE mains also.
No, इसलिए तो मैं नहीं पढ़ा रहा हूँ. मैं जबरन में एक्स्ट्रा नॉलेज आए, मैं ना इस साल मैंने डिसाइड करा था एक्स्ट्रा नॉलेज ज्यादा ओवरबर्डन करने से देयर इज नो पॉइंट, है ना.
Okay.
Chalo, anyways, thank you very much guys. This is it for today, and the next class will do something called as LC oscillations, which are there as a part of your syllabus, और उस पे थोड़े बहुत questions will do, and this chapter will be over. Okay?
Okay, sir.
Yes, sir.
Thank you.
ठीक.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.